So here we are in chapter 3, and we're going to be looking at water. So water is important because it supports all life. All familiar organisms are made mostly of water, or they live in an environment dominated by water. So even if you live in the desert, your environment is still dominated by water because water is such a crucial component. Even if you don't have a lot of it in your environment, how you manage and conserve that water is going to be key. So one of the things we looked at last time with water was these hydrogen bonds, and that's going to explain a lot of the properties of water. Water exists as a gas, liquid, and solid on Earth. So that may seem like, well, okay, not a big deal to you, but that's actually a pretty significant thing. Not many substances exist in all three states on Earth. Water is going to participate in reactions to sustain life. It's also going to be what makes up 70 to 95% of your cells and surrounds your cells. So water is a polar molecule. This is because of the unequal distribution of the electrons. This will result in the hydrogen bonding that accounts for these properties. So remember, this is the attraction of those partial positive and partial negative charges. These are some properties of water that help it contribute to life. It's got cohesion. The hydrogen bonds hold the substance together. This is important in plants. It allows water to move against gravity. It allows those water molecules to stick to each other. It will also have adhesion. So with plants, you may have heard of cohesion adhesion to allow water to move. The adhesion allows it to cling to other substances. This again helps it to resist gravity. Water is going to have surface tension. Surface tension is how difficult it is to break or stretch the surface of a liquid. And surface tension of water is higher than it is for most substances. Water will act to help moderate temperature. So it can be a heat bank where it will absorb and release large amounts of heat and only slightly change its own temperature. If you look at Puget Sound here where we live, you can have a significant change in the temperature outside, but you only have a relatively small change in the temperature of Puget Sound between summer and winter time. So it will actually absorb some of the excess energy in the summer to keep it from getting really hot here. If you compare the temperatures between eastern Washington and western Washington, it's going to be significantly hotter there in the summer. In the winter, it will be significantly colder because it's going to release some of the energy back in the winter to keep us from getting as cold. So the kinetic energy is the energy of motion. The faster the molecules move, the higher the kinetic energy. So water molecules will have kinetic energy. Heat is a form of the energy. It's the measure of the matter's total kinetic energy due to the motion of the molecules. So this will in part depend on volume. Temperature is the measure of heat intensity, so it's the average kinetic energy regardless of the volume. So heat is going to move from warmer objects to cooler objects. The heat is the energy, so that's what's going to move. Ice cools a drink by having the heat move into the ice cubes. If in the middle of winter you leave the door open to your house, the heat is going to move outside. It's not the cold air moving in. The calorie is a unit of heat. It's the amount of heat it takes to raise the temperature of 1 gram of water by 1 degree Celsius. So in the food industry, what they use is the kilocalorie, which is 1,000 calories. It's the amount of heat it takes to raise 1 kilogram of water by 1 degree Celsius. Joules is an energy unit, and 1 joule is equal to 0.239 calories, or 1 calorie is 4.184 joules. So the joules may be the energy unit. If you look at foods that are sold overseas, they will tend to use joules as the energy unit where we will use calories here. The specific heat of water is important as well. It's got a high specific heat, which is the ability to stabilize the temperature. This is the amount of heat that has to be absorbed or lost to actually change the temperature of 1 gram of the substance by 1 degree Celsius. So if we look and compare the specific heat of water at 1 calorie per gram per degree Celsius, or of ethanol at 0.6 calories per gram per degree Celsius, you would be able to see from that you would expect ethanol to evaporate faster than water. So if you were to have a pan of ethanol and a pan of water, and heat them up at the same temperature, the ethanol is going to evaporate faster. The specific heat of water is 10 times that of iron, so when you heat up a pot of water, the pot's actually going to get hot long before the water does in it due to the hydrogen bonding of water. With evaporative cooling, you have the molecule move fast enough that it will eventually escape and depart the liquid. So they start moving fast enough that they're eventually able to leave. When that molecule leaves, it's going to take its energy with it. So the surface of the liquid left behind will be cooler. So the hottest molecules have left. This is why sweating will cool the skin. So when the water molecule leaves your skin, it's going to take some of the energy with it and leave the skin behind it slightly cooler. So if you're in a humid place, your evaporative cooling is not going to be very effective because the air is going to have so much moisture in it, you won't have a whole lot of it evaporating going into the air. The heat of vaporization, this is the quantity of heat that a liquid has to absorb for 1 gram of it to be converted from liquid to gas. So in order to evaporate 1 gram of water at 25 degrees Celsius, you need 580 calories of heat. That's nearly double the amount it takes to do the same thing for alcohol or ammonia. So water can also insulate bodies of water. When you look at ice, it floats on top of water. For most things, as they get cooler, they are going to condense and become denser. And this will happen for a little while with water. It's going to get denser and denser until it gets to 4 degrees Celsius. At that point, it's going to start to expand because it's starting to form the crystals, and the crystals are going to occupy more space. So it will be slightly less dense as it falls from 4 degrees Celsius to 0 degrees Celsius. Then it will lock into the crystal lattice and the molecules will be held apart. So water is most dense at 4 degrees Celsius. This means that ice is going to float on top of water, and it will also insulate the water underneath and prevent it from freezing as easily. Sometimes water is referred to as the solvent of life. When you look at a solution, it's a liquid that's a completely homogeneous mix of 2 or more substances. So your solvent is going to be the dissolving agent, or what allows the substance to come apart. The solute is the agent that dissolves or dissociates or comes apart. So when that substance uses water as a solvent, we refer to it as an aqueous solution. So here, when we look at the sodium chloride, the sodium with the positive charge is surrounded by these waters with the partial negative charges. The chloride ion with the negative charge is surrounded by these waters' partial positive charges. So this forms what we call the hydration sphere, where the water molecules surround the dissolved ion. So when a solution is saturated, all of the water molecules are busy forming these hydration spheres. When there's no more water molecules left to form the hydration spheres, the molecule is not going to dissolve anymore and it will precipitate out. So a substance that is hydrophilic has an affinity for water. One that is hydrophobic is going to repel water. Colloids are kind of unique. They're a stable suspension of fine particles in liquid. To me, they kind of seem like they are the eternal snow globe. So you've got these fine particles, and unlike the snow globe, these are never going to settle out on the bottom. It's the snow globe that just keeps having the particles floating. So your solute concentrations are important in chemical reactions. If you're looking at a chemical reaction, you need to know how many atoms and molecules are involved in order to calculate the concentrations and to calculate the proper amounts of reactants to use. So we can use the mass to calculate the molecule in the experiment. Your molecular mass or molar mass is the sum of masses of all of the atoms in a molecule. So if you were to look on a periodic table, you would see that the mass of carbon is 12 and the mass of hydrogen is 1. So here we have methane, which is 1 carbon and 4 hydrogens. Its molar mass is 16. So you have 12 plus 1 plus 1 plus 1 plus 1. That's where you get the total of 16. So in chemistry, we use a lot of atoms. There's not just a few of them involved. And this is where Avogadro's number comes in. Avogadro's number is 6.02 times 10 to the 23rd. If you have a mole of something, it means you have 6.02 times 10 to the 23rd units of that substance. It would be like saying if you have a dozen of something, you have 12 of it. So when you have a mole of something, it doesn't matter what it is. There is always 6.02 times 10 to the 23rd units of it. Just like if you have a dozen of something, it doesn't matter what it is. A dozen is 12, regardless. So your molar mass is numerically the same as the mass of one atom in 1 AMU. So what that means is if we're looking at carbon, the mass of one carbon atom is 12 AMUs. The mass of 1 mole of carbon is 12 grams. So there are mathematical explanations for this that are really beyond what you need to know for this class. However, using the mole does make things much simpler for us in chemistry. So the molarity is the number of moles of solute per liter of solution. So how much solid stuff do you have in your liquid? So 1 molarity is going to be 1 mole per liter of solution. So if something is 2 molarity, it means you have 2 moles of it per liter of solution. If it's 5 molarity, you have 5 moles in 1 liter of solution. So if you have something that is 10 molarity and you've got 3 liters of solution, you could easily calculate out how many moles are in there. So in the lab, you'll actually have the opportunity to do some practice problems looking at the moles and some of the conversions. So acids and bases, these are going to occur when you have the water molecules separate into different parts. So your hydrogen ion is going to be when you have the hydrogen bond shift in the water molecules and the hydrogen leaves. So it's going to have a positive charge. Your hydroxide ion is going to be what's left after the hydrogen ion leaves. It's going to leave its electron behind, so that oxygen and hydrogen that are left behind will actually have a negative charge. So your hydrogen ion is actually the proton because it doesn't have a neutron with it. It's going to bind to another water to become hydronium. So that's the H3O+. By convention, we just write H+, but what we actually have is hydronium. So the separation of water is a reversible reaction. It's going to reach a state of dynamic equilibrium when the water dissociates at the same rate that it's being formed. So when it comes apart and goes back together at the same rate. In pure water, you're going to have 1 molecule in every 554 million dissociated. So when we look at the concentration of each ion in pure water, it's 10 to the negative 7th molarity at 25 degrees Celsius. That is going to come out to be a pH of 7. So we will look at how this comes about in just a couple minutes. So both the hydrogen ion and a hydroxide ion are very reactive, and they can drastically affect other molecules. So our pH scale goes from 0 to 14. So when something is acidic, what you're going to have is a greater concentration of free hydrogen ions than you do hydroxide ions. When something is basic, you're going to have fewer hydrogen ions than the hydroxide ions. And when it's neutral, you've got an equal concentration of both. So on the pH scale, 0 to 7 is going to be the acid end. And it's increasingly acid as you move away from 7 and proceed towards 0. Basic is going to be from 7 to 14. So it's increasingly basic as you proceed from 7 to 14 on the table. So this is the example of some things with their pH. So a lot of times people get a little concerned and feel that acids are dangerous and bad. Things that are strongly basic can be just as dangerous. It's more in biology about having the correct pH in the correct place. So a lot of times people get really concerned about battery acid. Gastric juice, which is in your stomach, and lemon juice are very close, and most people don't have too many concerns about that. vinegar, wine, and cola of pH 3, which is still pretty acidic, and we put those in our mouth pretty regularly. So urine, just under pH of 6. So, however, if you were to take lemons and put them in the openings where urine is, that would be an example of having something that's the wrong pH in the wrong place. That's when you run into problems. It's not that something that is acidic is inherently bad. So when you have changes in the pH, it's an acid. When acid dissolves in water, it's going to donate additional hydrogen ions. So in chemistry, there are different definitions for acids and bases that are both correct. In here in biology, we're just going to try and keep it simple with our definitions. So acids are going to increase the concentration of the hydrogen ion. Bases are going to reduce the concentration of the hydrogen ion in a solution. So they can directly accept hydrogen ions or indirectly by forming hydroxide ions. So a strong acid or base is going to be a compound that completely dissociates in water, and we indicate this with a one-way arrow when we draw out our chemical reaction. A weak acid or base, the binding and release is reversible. So there will be a fixed equilibrium ratio that you would have. However, the reaction is still reversible, and we indicate this with a two-way arrow. So your pH scale, this is going to apply in any aqueous solution at 25 degrees Celsius. The product of the concentration of the hydrogen ion and the hydroxide ion is going to be a constant at 10 to the negative 14. So if you multiply the concentration of hydrogen ion and the concentration of hydroxide together, you get 10 to the negative 14. So in a neutral solution, hydrogen ion is 10 to the negative 7. And hydroxide ion is also 10 to the negative 7 molarity. So when you multiply those together, remember when you are multiplying, you are going to add these subscripts together, or these superscripts together. So the negative 7 plus negative 7 will give you negative 14. If you increase the acid, you increase the hydrogen ion. So for example, if we increase it to 10 to the negative 5 molarity, remember this is actually a bigger number than 10 to the negative 7 molarity, then your concentration of hydroxide is going to decline to 10 to the negative 9. So being that this is a constant, if you increase one of these numbers, you're going to have to decrease the other. So when you're looking at the pH of a solution, it's going to be the negative log to the base 10 of the concentration of the hydrogen ion. So because it is a logarithmic scale, each whole number change reflects a tenfold change. So your pH is negative log to the base 10 of the concentration of the hydrogen ion. For a neutral aqueous solution, that concentration of the hydrogen ion is 10 to the negative 7 molarity. So when you take that and you multiply the negative times the negative here, it's going to become a positive, which is why the pH is 7. So in this class, you're not going to have to worry about calculating out the pH, but what I do want you to understand is that it's a logarithmic scale. So for each whole number change, that's the tenfold change. If you go between a pH 6 and a pH 5, pH 5 is 10 times more acidic than pH 6. pH 4 is 100 times more acidic than pH 6. pH 3 is going to be 1,000 times more acidic. So it is going to increase logarithmically as you move out. Same thing if you went in the other direction for something that is basic. Something that is a pH 12 is going to be 10 times more acidic than or 10 times more basic than a pH of 11. pH 13 will be 100 times more basic than pH 11. So buffers are going to be substances that minimize the change in the concentration of the hydrogen ion or hydroxide ion in a solution. So what they will do is accept the hydrogen ions when they're in excess and donate them when they're depleted. So buffers usually have a specific range that they will work as a buffer and help to absorb some of the change. This is important in biology because a lot of times pHs are going to turn things on or off. and you don't want to have things get turned on and off too easily. This will help keep things from being too reactive. So usually buffers are going to contain a weak acid and a corresponding base. So when we look at threats to the water quality on Earth, acid precipitation is rain, fog, snow, anything that falls out of the sky with a pH less than 5.2. So burning fossil fuels is going to release sulfur oxide and nitrous oxides. These will get dissolved in the precipitation, and then when the precipitation falls down to Earth, it will carry the pH change that corresponded with it. Carbon dioxide gets absorbed by oceans, and it will react with seawater to form carbonic acid, and then that will dissociate to make bicarbonate and carbonate. This can end up affecting corals and other organisms. So if you were to take some chicken bones from your dinner and soak them in vinegar, you would actually see a change in the bony structure in there. The bones will become soft and pliable. So we know that this will affect the oceans, and we've been able to see what happens when you have a significant amount of this acid being dissolved in the ocean by looking at what's happened with volcanic vents under the sea. So if you look down tide from those things, you can actually see their impact on coral reefs and sea life in that area. So that is the end of chapter 3.